Very good evening to everyone here. Good morning, good afternoon, good whatever. Because some of the people watching may be in the North Pole, South Pole, or on the top of Mount Everest. Right. So we have here from the Astro Society of Penang. Three of us will be presenting our APOD. So we are the APODers, Astronomical Picture of the Day by NASA. Right. So introduce our Miss Chiu Boon Wei, okay, on the left, and our Rayan Akadri on the right. I am Dr. Chong, right? So basically, Boon-Wei and me, we are in Penang, and Rayan is somewhere further south in Kuala Lumpur. So for those who are not aware, so we are actually in the peninsula of Malaysia, a country which is north of the equator. So we are actually to the north of what you call Java, east of Sumatra, south of Thailand. All right. So that's where we are. So we are talking about airport. So this is our what you call 25th of September. So before I start, so Ryan Bunwei, you know what's important for today? 25th September, you should know. Know your for me. We have already two days after the event. What's that? 23rd of September, 2 days ago on Friday was autumnal equinox.
Yeah, I know that.
The sun was moving from the northern hemisphere, crossing the equator, going to the south. So as the days pass by in future, the northern country, because the northern hemisphere will be colder. And then countries in the southern hemisphere will be warmer. But for us in Penang, in KL, just above the equator, not much difference. But for countries in northern Asia, in India, China, in Russia, in Europe, in North America will be colder as time goes on. So it's our autumnal equinox, right? For us, it's not much. For us, only a rainy season or dry season in
And
Malaysia.
of course,
Yes.
the day and the night on this autumnal equinox happens to be the exact same duration of time
Yeah. Everywhere in the world.
everywhere in the world.
Equinox. Of course, there's another type of equinox is our spring equinox, also equal time, but that is in March 21st, 23rd. Yeah, good. Thank you for the reminder. So I'll share my screen now for airport, which is 25th of September. So can you see my screen, Arian?
Yes, we
Okay.
Yes, we can.
Yeah. Oh, Perry. That's a Perry in the Eagle Nebula. So let's go to the Perry Eagle Nebula. Yo, so big. You look at it. Very big, you know. Wow. Right? So Perry or Eagle Nebula. Well, image Perry, of course, is by NASA, ESA, European Space Agency, Hubble Heritage Team, and SCSCI. Of course, SCSCI is the famous Space Telescope Science Institute in the University of Johns Hopkins, Baltimore, America, where the Hubble telescope is based, and also the James Webb telescope is based. AURA is a kind of professional astronomy consortium in America. Okay, so that's big. So I'll make it smaller. Okay, not small. Now it's so long. That's one. It's long because 10 light years in length. Huge, right? So this is in the constellation of Serpens Caput. Very interesting name for a constellation, Serpens Caput.
yes.
Meaning the serpent or the snake, right? So remember, this is the theory of the Eagle Nebula, not the Eagle Nebula, the theory. Remember 1995? I don't know whether Rayan, you are born or not. I think Google was born. The famous Eagle Nebula, M16, Messier 16, in constellation of Serpens Caput, all right? Eagle Nebula. So this was a defining picture of Hubble, one of the most famous picture. But even the American newspaper call it the pillars of creation. Some added even more fantastic, the fingers of God, right? So this is the Eagle Nebula. So this serpent eagle theory of the Eagle Nebula is not exactly that. It's over here. Okay, now that I'll make it bigger now. Okay. So now this is the Eagle Nebula where the cursor is showing here. And here is the belly of the Eagle Nebula. Okay, this is one. In the same field of view, very beautiful. So basically, what is it? So in short, I call it stellar nursery. So in Malaysia, we call it Tadika Bintang. The stars and the planets are being born. and maybe aliens will be born in there. So look into detail the what we call this theory of the Eagle Nebula. Very big. We make it smaller now. 10 light years in length, right? So basically, what happened is that you have the stars and that died earlier, generation died. So the gas and dust was blown off. So it will wait until long time. It will collapse, and new stars will be born. But the problem is this: that you see some of the stars here in embedded in this cloud of dust. They're just being born, so they will blow out very powerful stellar wind. It's just a solar wind, but our sun's solar wind is very gentle, very mild, very slow. But this can be up to hurricane force. So what's happening is that you have here a 10-kilometer length pillar of dust trying to collapse to form new stars and new planets. But then there are nearby stars that were born earlier will evaporate. Evaporate means it will blow away this gas and dust, such that given about 100,000 light years, 100,000 years into the future, if these stars are still there, so their stellar wind will blow away this what we call theory of the Eagle Nebula, so that it's no more there. So there's now two types of forces. Gravity will try to make more stars be born, but then the stellar wind, which is stellar wind, basically the stellar particle from the emitted by the stars, and also the stellar wind, stellar radiation, the light radiation can blow away, evaporate. So this is it. So it's a famous theory of the Eagle Nebula, right? So very nice, right? So basically, you will say that they're going to fight here. Whether see how many stars will be born. So if you ask me how many stars can be born now, remember this 10 light years in diameter, no? You add up, it could be many thousands of cubic light years. So maybe here it could be few 100,000 stars can be born from here in future. But of course, we know that this thing they simulated with a supercomputer that a cloud of dust can collapse to have new stars being born. So it seems that only 1% of the material in the gas and dust in this stellar cloud will successfully collapse to form the new star. 99% will be blown away. But that 1% is good enough to form the stars. Okay? So now I pass over to our presenter now. Rayan, what to you?
Okay, let me share my screen.
I'll unshare my screen. John?
Can you see my screen?
Yes.
Okay. Can you see when I go here?
Wow, nice.
Okay. One moment. Let me get back.
Very rare.
Okay. Now my first APOD for this session is the picture for September the 18th. Analema over the Kalash stones. Now this image was taken by Giuseppe Petrica. He is a mechanical engineer who is a technical support staff for a group called the Raspberry Shake. What they do is create these portable and affordable meteorological survey devices. So basically seismographs that can fit inside a bag very easily, not the big chunky ones that meteorologists use. Now, he also has a hobby of astronomy, and he likes to take these images. He's currently studying for a master's in energy engineering at the Lewis Castle College in Outer Hebrides, or the Western Isles of Scotland. And less than, actually around half an hour away from this college, are what we see here, the Kalash stones. Let me head out here. The Kalash stones are an arrangement of standing stones that were erected a few hundred years before another very famous group, Stonehenge. Stonehenge was formed and was erected a few hundred years after these Kalash stones here. So that's enough about the stones. What is going on up here? Well, let me zoom in to help you see. You see those dates there? We've got, let's see, 25th of March, 4th of April, 20th to 26th of April. These are all dates on which a picture of the sun was taken. So what we're looking at is something called an analemma. An analemma is what happens if you were to take an image from the same angle on the same place on Earth at the same time every single day. And as long as that frame captures the sun, well, it doesn't have to be every single day, every certain interval of time, but as long as every frame has the sun in it, you will get an analemma. And it comes, yes, in the form of a figure 8. So why is it a figure 8? Well, let's review what we know of the Earth. We've got the sun here, put an S there. We've got a smaller, again, this is not to scale, but this is going to be our Earth. Now, Earth orbits around the sun. That we all know. What you may not know is that if we were to imagine this as the orbit of the Earth, you might think that if this were the Earth, we spin along this axis. So we spin this way. That is in fact not true. What happens is, this is our plane of orbit, okay? So the Earth goes from here to here as you're moving as you're moving around the sun. But the Earth actually has a tilt, an axial tilt, we'll call it, here. So the way it spins around, the way we get our days, happens in this direction. And this angle here is about the angle of our axial tilt is about 23.4 degrees. So what this results in are our seasons. It relates to this analemma, but it also relates to the seasons. You see, if this is the sun here, the Earth could be at this position here with the tilt facing this way. At the same time, 6 months later, the Earth would be here, but the tilt will be this way. Our North Pole is here. Our South Pole is here. Mark that in red. North Pole here, South Pole here. So, and this is exactly how we get our seasons. Why is that the case? The sun shines its light, and it hits right here and right here. That means that for one portion of the Earth, for one hemisphere, you will get days that are longer than their nights. And for another portion, you will get nights that are longer than days. When your days are longer, you get more sunlight. And that's when you have summer. When the nights are longer, you have winter. As we mentioned earlier, there's something called the equinox. The equinox happens when the tilt is just right that the day and night match. But what's important to understand here is this axial tilt. That means that the sun changes its position. It will go from very high at the summer solstice to very low at the winter solstice. But then we ask, why is it in this figure 8? Why isn't it just a straight line? Well, that's because of another feature of the Earth, which is its orbit around the sun. We orbit in an ellipse. That's a bad ellipse. Let's fix that up. We orbit in an ellipse. And what that ellipse means is that at one moment, the Earth could be here and is moving very fast. But when it's here, it moves slower. Why is that? Newton's second law. The area from the Earth to the center of the sun, or whichever object it's orbiting, must match through whatever length of time. For that reason, we move slower at our aphelion, when we're further from the sun, and faster at our perihelion, when we're closer. And that's what we see here. This portion here is when we're at our perihelion. This portion here is when we're nearing our aphelion. This results in the figure 8 that we see. Now, for some of you, if you're familiar with the idea of sundials, you may know that sundial time is rarely the same as your actual clock time. This width here determines the difference. So here we have a very wide difference between sundial time and clock time. But here at these intersections, these are among the days where it happens at the same time, meaning what time your sundial tells you is the same time that your clock tells you. Now, talking about how this image was taken, it is nearly impossible to get a vertical analemma and also have a landscape to show, unless it's Photoshop. Now, I'm not saying this is Photoshop, because I have a theory of how a photographer here took the image, how we get this analemma. Now, first, why is it impossible? Well, the only way for you to get a vertical analemma is for the image to be taken at noon. And if it's taken at noon, your sky wouldn't be this dark. So why and how, more importantly, how do I think he did it? What I think he did was first took a vertorama. This is what we have here. A vertorama is a vertical panorama. It allows you to see from this landscape down here all the way up to the sky above. And then I think at noon, on each of these dates here that the images were taken, Giuseppe took a picture of the sun. He then removed the background for all of them, overlaid it, and ended up with this beautiful image. Now, it is, of course, possible that he rotated the analemma, but I highly doubt that was the case. That would be much, much more difficult to do. So, that is my first image. That is analemma over the Kalanash stones. Let's now move on to my next image. The APOD for September 15th. Harvest moon over Sicily. Now, whereas Signor Petrica created a vertorama, here we have Dario Ginobili, who, instead of creating a vertorama, used a telephoto lens, which basically enlarges and makes any distant object look closer. So, using this telephoto lens, he came up with this image. So what do we see here? Well, first, this image was taken on September 9th and has two main themes. The first is of a little commune called Castiglione di Sicilia. It is an eastern commune in Sicily. For those of you who are familiar with the Godfather movies or have heard of them, there is a scene in the first Godfather film where Michael is getting married in Sicily. The place where they shot that scene, Forza d'Agro, is actually about an hour drive from this eastern commune. It's also in Sicily, but in a different city. So, besides this commune, what else do we have? Well, we have a moon. More precisely, a full moon in September. Now, September full moons are called harvest moons. And because this image was taken around moonrise or sunset, it appears reddish in hue. We've covered this before. It's basically because there's a lot of air between the observer and the moon, and that air causes scattering of the blue of the light from the moon. So the sun shines light on the moon reflects it onto Earth, and that light, the blue, gets scattered away so that all we're left with is the red light. That's how we get this effect. Now, as for why it's called harvest moon, I think it's actually it's pretty interesting why we call it a harvest moon. It's also called a full corn moon or a barley moon because this is towards the end of summer where a lot of the crops are harvested. Because the moon rises early and is pretty bright, the moonlight itself is able to give sufficient, it's able to light sufficiently for the farmers so that they can even continue harvesting into the night. They don't need to wait for the next day for them to continue with the harvest. So here, this is harvest moon over Sicily.
Beautiful picture, very nice picture.
Yes, it is. Okay, now my next APOD is for September 12th. This one is pretty interesting. I'm going to need to go into Creta. Okay. About a week or two before the previous image was taken, photographer Daniel Shacherba took this image at the Ruby Jeseník. It is the second tallest mountain range in the Czech Republic, in Czechia. Now, the main focus of this image are something called red sprites. Red sprites, right. Red sprites were discovered in 1989. In this image, they're about 200 kilometers away from Pane Shachurba. But what are they? Well, red sprites are part of a group called TLEs, transient luminous events. Another prominent member of this group are halos. We see a lot of halos on APOD. They are a type of TLE, similar to these red sprites. So what are they? Again, I ask. Well, imagine this. It's a particularly stormy night, and there is a sudden horizontal strike of lightning. It strikes across the sky horizontally. And because of how heavy this storm was, how powerful it was, which is usually positively charged, turns the ground below positive. So it turns this positive. But at the same time, it turns the area just above it, which is about 12, 15 kilometers above the ground, it turns this negative. So this part becomes negative. Now, just above it, in the lower ionosphere, right around the Kármán line, actually, 100 kilometers. Let me mark this here. This is around 15 km. And here we have something up here, really high up, at around 100 km. The area is generally positively charged. So we get positive charges. Now what happens? There is a sudden imbalance between the two areas, which results in something similar to lightning. It's not considered lightning. What happens is we get a sudden surge. These surges travel at about 10% the speed of light, and they are what you see as these red sprites. So the sprites usually occur at a height of 80 kilometers above the air. So this 100-kilometer line should actually be somewhere up here, but for the purpose of this presentation, I'm going to write it in over there. That's where it's in between this area that we get these red sprites. Now, they appear red due to the similar process as auroras turn their colors. What do I mean? When an atmospheric particle gets energized, it gets excited, it releases out light in a specific wavelength. Now, that wavelength is determined by the element that this atom belongs to. Usually, above 100 kilometers at the height of auroras, there's a lot of oxygen, not that much nitrogen. So you get green light. That's why the majority of auroras you see are green in color. But at this height, where the sprites occur, it's mostly nitrogen. Now, if we were lower down where you have high pressure, the nitrogen being excited would turn blue. But because we're in an area of lower pressure, it turns red. So that's why you get these sprites turning red. Now, they aren't really rare. They aren't rare. Red sprites are not rare. But they last for only a few milliseconds, and they only occur during heavy thunderstorms, really powerful thunderstorms. They are the only ones that are able to create this difference, this great difference in the charges. But once you can see them, though, they are just beautiful and actually very big. These red sprites can get to sizes of around 50 kilometers by 50 kilometers. Just for scale, that is around the area of Penang Island, but over 2 times. Not just Penang Island and Penang mainland. You combine them together, you need over 2 of those to get the area that a sprite can take up. 50 kilometers by 50 kilometers. They are enormous. So the next time you are a heavy thunderstorm appears at around 200 kilometers or 300 kilometers away from you, just stare into the sky for about 30 minutes. And you may very well catch these sprites, these red sprites, because I'm not kidding, they can be found anywhere. They've even been spotted in Malaysia.
Yeah.
You just need to watch out for long enough. Now that brings me to my final APOD. The APOD 4. Where are you? September the 9th. Interstellar Voyager. This is one of my favorite APODs. Now, what are we looking at here? Unlike the majority of APODs that we usually have, and actually like the rest of the APODs you're going to see today, this is not an image taken by a camera. No, this is a poster that was rendered by a group of artists and designers at NASA's Jet Propulsion Laboratory, which is located in Caltech in Pasadena, California Institute of Technology. So Jet Propulsion Laboratory, JPL, has a group of artists and designers called the Studio. And in 2017, they made this. It was originally to celebrate the 40th anniversary of this object here, but for the purpose of this year, it's to celebrate the 45th anniversary. Now, what is this black object we see here? It is probably, no, it actually is two of mankind's greatest achievements. Why do I say that? They have traveled further than anything artificial ever has. They have given us some of the most beautiful planetary close-ups, stuff like this. An image of Neptune we're probably all familiar with. It has even shown us how small our planet Earth is. It has discovered moons and rings we did not know existed. And on board each of these things is a golden disc that could possibly become the last record of humanity millions of years from now. As you've seen, yes, I am of course talking about Voyager. Voyager 1 and Voyager 2. Since they're physically identical, this poster can be used to refer to either Voyager 1 or Voyager 2. So there's a lot of information that is explained here. I'd like to talk about some of the stuff that aren't explained. It was launched in 1977, about 16 days apart, and they had different trajectories. Let me explain. Voyager 1 used two planet gravitational assists. The reason the Voyagers had to be launched at that exact time was because of a perfect alignment of the planets that only happens every century or so. Now, what am I talking about? This is Earth. Voyager 1 gets launched. First planetary assist comes from Jupiter. Passes by Jupiter, taking an image of it. That's how we discovered that Jupiter had rings. And then it passes by Jupiter, and then it travels to Saturn. And right after that, it took off out of the solar system. It has actually left the solar system. It left the solar system in 2012. Now, Voyager 2, on the other hand, had a different route. It still did pass by Jupiter, though Jupiter would have been further in its orbit. And then, of course, it passed by Saturn, which would again have been further in its orbit. But right after that, it went to Uranus. And then it went off to Neptune. It took a picture of each of the 4 gas giants in detail. Only then did it leave the solar system. So because of this extended route, it left the solar system in 2018. Launched in 1977, I remind you. They only left the solar system in 2012 and 2018. Now, one of the gravitational assists, one of these four, actually slowed Voyager 2 down. So while they both had the same starting speed, Voyager 1 is traveling at around 17 kilometers per second, while Voyager 2 is traveling at 15 kilometers per second. Now that is quite a difference, but I mind you, it is still faster than 50,000 kilometers per hour. Most of the cars nowadays, they max out at what, 200, 208? No, around the 200s, let's say, as an example. We're talking about over 50,000 kilometers per hour. Or for those who use the imperial system, 31,000 miles per hour. So yes, they are very fast. Now, my favorite image from Voyager 1 is something called the family portrait. Let me see if I can find it. The family portrait was an image taken on Valentine's Day in 1990 when, there we go, when Voyager was about 6 billion kilometers away from the Earth. What we see here are images of Venus, Earth, Jupiter, Saturn, Uranus, and Neptune as seen from Voyager. So this was their relative position from where Voyager could see them. There they are: Jupiter, Earth, Venus, Saturn, Uranus, Neptune. And one of my particular favorite images is one that Carl Sagan fought very hard to take and advertised and has mentioned very often: the pale blue dot. That dot in the middle of the band is Earth. That is where Earth is. Look at how small it is. Everything we have lived through, everywhere we have gone, everyone we have spoken to is on that small little dot in the vastness of space. Now, the other thing that Voyager carries is the golden record. As I said, it could very well become the last record to exist millions of years from now, the last record of Earth and of humanity. On the record itself are instructions of how to play it. There is a needle and some other equipment on board the spacecraft to assist in alien civilization who happens to find this and happens to play it. Now, what is on there? Well, we have 115 images of humans, of Earth, of life, of nature on this disk. We also have 55 greetings in 55 different languages. So a greeting from various countries, and we'll talk about 55 of those, so 55 different languages worth of greetings. At the same time, there are 27 different songs, classical and such, and also 21 sounds: animals, rain, vehicles, humans, laughter, basically life. Now, it's coated with uranium, not to make it radioactive, but to be used as a timestamp to know how much time has passed since it was launched, since when an alien civilization finds it, if they ever find it. Because the golden record will be playable 1 billion years from now. Much could happen by that time. If by the slim chance an alien picks it up, they will have to be civilized first, civilized enough and technologically advanced enough to have even found it, which means they should be able to read it. It is our duty to ensure that after they read it, if it is not past the end of the earth, that we are still here. Because as Sagan mentioned, they will wonder after going through this, has has their technology overpowered their wisdom? Have they destroyed themselves? Or have they gone on to do better things? And it is our duty to make sure it is the latter. I apologize if it's getting too somber or too dark of a note. And on that, I will pass it over to Bunwei.
Yeah.
Yes, it was a good presentation. Okay.
Thank you, Dr. Chong.
Oops, hello. So let me share my screen first. Can you see my screen now?
Yes. Wow, so nice. Oh.
Yeah, this is the picture on the 19th of September.
Yeah.
So this picture is so, I feel is so majestic.
Yeah.
And yeah, so the title of this picture is Star Trail and Lightning over the Pyrenees, taken by Mark Limus, the photographer in Osona. So as the caption and the explanations said, that the beauty in this image is come into the layers. So you can see this picture has one, two, three, four layers, and the bottom layers is actually the village of Melil in Barcelona, Spain, and Mark he took the 6 minute exposure, so you could see the car light is into the stripes. So this is the first layer, and the second layer is the famous Pyrenees, is the Sierra de Melman. This is the mountain range that's threading the border of France and Spain. And the third layer, it looks like the nuclear bomb. So this is the thunderstorm, and usually it's called as the anvil cloud or cumulonimbus cloud. So how this anvil cloud form is actually, you can imagine like the boiling water. If you open the pot, and the steam will rise up and then spread out on the ceiling. So the cloud is also do the same thing. The clouds it updraft to the tropopause, like our Earth atmospheres. It has five layers. So the bottom is the troposphere, and then the second layer is actually the stratosphere. So when the clouds that updraft onto the tropopause, meaning the bottom of the stratosphere. So up there will be the stratosphere already. So these clouds, they immediately spread on um, the tropopause, because the temperature is cold there. So now, if you see the larger the cloud, and meaning the thunderstorm is very very large, so pilot will always try to avoid this kind of cloud. And in this picture also, you can see there's a lot of the lightning bolts, because of the long exposure on um, taken. So the top layer, the above the stratosphere, you still can see the star trail. So this star trail is actually can indicate that the distance from the north spin pole of the Earth above. But it seems like its curvature is quite not so round, so it should be still not near to the northern sphere. Yeah, so according to Mark, this actually taken after the sunset in the early June. Okay, so this is my first picture, and the next picture is this one. Is APOD on 4th of September. This is also very very nice and beautiful, with the Milky Ways and also the growth of the light. yeah, so this photo is actually the old composition picture captured in mid 2018 at Myers Creek Beach in Oregon, USA, by Ruby Montoya, the photographer. So you see here, the right side of this picture, you can actually see the blue glow. So this glow is the bioluminescence glow. So it's actually the production of and the emission of the light by the living organism um, through some chemical reaction, and it's actually produce the light energy within the organism body, and after the light grow, then the organism will be dead already. So um, normally when the surf, I mean on the beach, right, when the surf hits the beach, then the the lights will be growing and creating this kind of the scene. So uh yeah, so at this center, this one is actually the volcanic stack. So this was formed by the you see the sculpture of the rock is actually formed by the wave erosion, and over the time by the wind and the wave. So this is kind of the process of the coastal geomorphology. It's very nice, and you build the rocks into different shape, and this is the foreground, and separate this picture like into two half. One right side with this blue glow, and then the orange light. The orange light is you can see is quite blurry because there's a thin fog layer, so it's actually scattered the lights on the horizon already, and the rays of light from this is actually from the fishing boat very far away. And then here, this is the lights from actually the car headlight on the US, the highway 101, the north south United States numbered highway that actually run through the states of California, Oregon, on the west coast of the United States. So behind the state, behind the stacks, this the volcano stack, you can still see the beautiful Milky Way galaxy. So it's appearing to like racing from this dark rocky, this rising from the dark rocky outcrop. So basically, to take this photo, um, Rudy, he actually stacked 16 images to bring up the background of the Milky Way, because the stack he need to like taken in different exposure, then the composition as well. So he stacked 16 images to bring up the background of the Milky Way, and also the to reduce the noise from the other lights. Okay, so the next one is my last APOD today. Is the okay. So this is the 3rd of September APOD. This is the sun and the moon and the ISS. Yeah. So this photo is actually taken on August of 25th, when the sun and the moon is axis together during the daytime. So I think the photo is taken like one by the Wang and then one by Jinma at two different district in China. So uh, the moon is taken by Jinma. He is from the Beijing Planetarium, and then Wang is from, he took the sun is from the Fengtai district, is actually about like 40 kilometers to the southwest. So at like about 29 seconds later after the ISS transit the moon, then the sun then the ISS transit the sun at Feng Tai district. Yeah. So from this photo, actually you still can see the sunspot, a few sunspots here and some filaments here. Yeah, and the photographer put these two ISS transit compared into panels, and also they process and stack the video frame together and then make them into like one scale. So they also make some calculation for this solar and the lunar transit at the sun. They actually calculated range of the transit is about 435 kilometers, while 491 kilometers passing in front of the sun. So another one is the 435 kilometers for the lunar transit. So if you would like to capture the ISS or you want to see the ISS, actually you can also go to the this one, the spotthestation.nasa.gov. Then you can also key in your location and see where's the ISS. But it seems like Penang cannot get the sighting opportunities this week. Yeah. So normally when the ISS across the sky is like a moving star moving across like very slowly, something like this. Yeah, so that's all for me for today. I pass back to Dr. Chong.
Thank you, Boon Wei. Unshare your screen first, Boon Wei. Thank you.
Okay.
Can see my screen, huh? Okay. So 17th of September, all right. Perseverance in J0 Crater Delta. Of course, Perseverance is the latest NASA Mars rover. All right. So that's it. Okay. So this picture, to me, has been presented years ago. Remember, 1997. There was a talk in Convent Green Lane Secondary School. At that time, the American rover Sojourner landed on Mars, So those days, 1997, first American rover on Mars. First rover ever on Mars. But now there are so many. Now it's our Perseverance rover, and it is actually by NASA, Jet Propulsion Laboratory, Caltech, MSS. MSS is the famous kind of private company, Marine Space Science System. And ASU, of course, is our Arizona State University, heavily involved in space exploration. Okay, so Perseverance in J0's Delta crater. So basically, it landed in this crater, which is a delta of a river. Remember, you have a river, let's say the Nile River, that flows through this Sudan, through Egypt, and go into the Mediterranean Sea, and that's a delta. So they say that Mars, billions of years ago, got liquid water, and this Perseverance is landed on a J0 crater. Previously was the delta of a river, so most likely to have life. So the remember J0 is a very big rover, 1 ton, like a proton villa, big one. And then on it you have equipment that look for conditions suitable for life, and also look for the biosignatures. When you can see this type of thing on Mars, maybe have life. And also J0 crater, Perseverance rover also got it. You will dig the soil of Mars and will encapsulate and bury somewhere in the Martian soil. The future American and European Mars mission will go and retrieve those capsules with a Mars rock and come back to the Earth. All right. So this is very nice. All right. So basically now we are actually trying to look for actually life. So we hope that some of the sample returned by this NASA mission, and hopefully the future Chinese mission, come back to Earth, they find, yes, there is somewhere there's a life. Let's say that they see somewhere in a piece of rock a fossilized amoeba or fossilized paramecium, all right, a single cell creature, or maybe a fossilized worm from Mars. So it could be, you may say, we are very sure that there's no life on Mars. Are you sure? So now scientists are not sure, because some of the places that the earlier rovers landed, or some of the Mars landers landed, maybe they landed in the place where there's no life. But maybe in other places got life. You never know. So this is where previously got water. So most likely, if there's any place that can life, is in Jezero crater. So Jezero now is still working. Remember, it was launched and it landed, and then it's still working now. And a lot of data are still coming back. All right. So we can follow these Jezero rovers with information back from Mars. Okay. So the next one is September the 13th. Okay, so I read, yo, there's a snake, I make it small later. A long snaking filament on the sun. So this is our Alan Friedman. Now he is has a company called Averted Imagination. So basically, this is a false color imaging of the solar surface. I mean, if you see with your eye in visual light, it doesn't look like that. So the wavelength has been changed so that to enhance certain feature, right? So he's from Buffalo, New York, right? He has a company called Averted Imagination, and he's famous for taking pictures of the sun, right? So I'll make it smaller now. Okay, so basically you see here a long filament on just above the sun surface. So basically, remember, the sun surface has three types. The lowest part is the one that we see with our own eyes, called the photosphere, visible light. But just above the photosphere is the chromosphere, the pinkish color one. So basically, this is looking at the chromosphere. And above the chromosphere, there's another one, which is, the name is something like, between the chromosphere and the corona, you have a third layer. So this is the second layer, the chromosphere. And there above it, you have a long prominence. And here you see, at the edge, there's also another prominence. So this prominence and this prominence are the same in nature, except that this prominence is actually between us and the sun surface. But this, we are looking at the prominence edge on. So nice to look like a snake, all right? And it seems the length of this filament is about half the radius of the sun. And this bright spot here is a sunspot. So in other words, the original color is black, but they make a negative of it become bright. The size of the Earth. Remember, we can put across the diameter of the sun 100 Earth. So 100 times 100 times 100, a million. You can put about 1.3 million Earths inside the sun. So this is about one Earth. So it shows that how small is the Earth, right? And yet, the sun is called by astronomers a yellow dwarf star, a small star. So imagine we put our Earth across the disk of Betelgeuse, the red supergiant. Remember, Betelgeuse is a few thousand times bigger than our sun, So you compare the disk of Betelgeuse with our Earth, Earth will be very puny, just a dot here, a point there. So this is the sun, and with the Earth here, and look at the details. And remember, this is only a still picture. The raw data could be in the form of a video. So you can see the video. You can see all the changing there. Right? So I always say that we compare the surface of the sun. It's as if, like, let's say, you put coffee oil, this is black coffee, you stir in pour in some milk, and you stir it, and the coffee is still hot. You see a lot of action on the surface of the sun, just like the milk moving on top of the black coffee, right? So the long snaking filament on the sun. The next one would be 7th of September, not 8th of September. I read here, North America and the Pelican. All right. So let's make it bigger so that we read the accreditation belongs to who, took it, and so on. Okay. So this is by our, okay, I repeat, North American Nebula is here, Pelican Nebula is here, and by our Hare, Frank Secondhand. So rain in Germany, Mr. So and so is actually Hare, H-E-R-R. So Hare is Frank Seckenheim is a German astrophotographer. All right. So basically, you see here, this is our North American nebula, okay, and the Pelican Nebula in Cygnus the Swan, and he actually is from Cologne in Germany. So look at the name of his website. I like the name of the website. Just have a look at the name of the website. Okay. So that Astrophoto Cologne, Deep Sky Astrophotography by Planck Secondhand. Now remember, he's from Cologne, you know. So I don't know whether some of you use it. Sorry, Bunwei. For the men, for the ladies, you put perfume, but some men they put cologne. You know, a cologne is a type of thing you apply on yourself to look and feel better. And so he called his website Astrophoto Cologne. Very nice. All right. So that's it. So now we go back to the picture. All right. So basically, North American Nebula in Cygnus, and you look carefully. Actually, the shape of the North America is not so clear. Let's go into another website. You look at the North American Nebula, it's very clear. And compare with our picture. Yeah, you saw that? Okay, on the right side, you see. So look, this is the right side, a more clear version. This is his picture. All right, I make it smaller. Okay, by Frank Seckenheim. This by another person. So this is North America, and this is pelican. Pelican is kind of a bird with a big beak, B-E-A-K, beak. Okay, so this is North America, meaning this is Canada, this is Florida. Somewhere on the left is California. This is Mexico. This is the Gulf of Mexico. So North American Nebula, and this is a pelican. So we know, Bunwei and this Rain, welcome to the Astronomical Zoo. A lot of interesting names given to this astro object. So welcome to the Astronomical Zoo, or something called the Zooniverse. Okay. So this is the picture by Seckenheim. This is our North American Nebula and the Pelican Nebula. So not easy to take, not something object. You need a long exposure, a lot of time to take it. But so nice. And I remember nowadays, many years ago in airport, they will tell you what telescope the guy was using, how many long exposure, what camera was using. But now, no. Now assume that anyone who takes a picture accepted the airport, they're expert in photography. No need to do it. So instead, talk about the object itself. Okay. The next one is 7th of September. This is the one. Okay. Tarantula stars. No, this is the second one from Webb, Rain. Tarantula stars R136 from Webb by NASA, European Space Agency. CSA is a Canadian Space Agency. CSCI, which is our Hubble telescope and Webb telescope, and Webb Euro production team. All right. So look at it. Now, what's Tarantula Nebula? Somewhere, I think, in the last Magellanic Cloud, the dwarf galaxy, what we call orbiting our Milky Way to the south, or sometimes called one of the two sidekicks of the Milky Way. The two sidekick, you know, sidekick means you have the hero in the movie, and then the hero, there's a small boy or girl, so the sidekick. So our Milky Way got two sidekicks. One is a large Magellanic Cloud, one is a small Magellanic Cloud, and in it, you have this, what we call Tarantula Nebula. Now, this one doesn't look too much like a tarantula. Tarantula is a so-called dangerous, poisonous, big spider from South America, right? But if you look at some of the other pictures taken of Tarantula Nebula, it really looks like tarantula, all right? So this is a Tarantula Nebula, and in the what called in the sun sky, in the large Magellanic Cloud, and you see here a star cluster. See so much information here, okay? Tarantula stars R136 from Webb. So remember now, Bunwei and Rain, we don't say from the James Webb Space Telescope. No, from now onwards, it's going to be Webb. That means James Webb Space Telescope. Okay? Remember, years ago, in 1995, when internet came to USM, we present a lot of Hubble telescope. I'll say, this is a picture from Hubble Space Telescope. From Hubble Space Telescope. Many years later, it's only Hubble. So So now we must get used to it in the future. All right. So now the next one will be the last one for me, 5th of September. This is again from there. Just look at this. Woo-hoo. Okay, I make it bigger so you can see. Kalina Kiss from the Webb Space Telescope. Again, NASA, ESA, Canadian Space Agency, SCSCI. SCSCI, remember, is the Space Telescope Science Institute. It's in the University of Johns Hopkins in the city of Baltimore. And Baltimore is not very far from Washington, D.C. Okay, so now is that it's similar to the earlier we saw. Okay, the so-called fairy what they call dust cloud in this what they call Eagle Nebula. Okay, so basically here is remember Webb is taking infrared, and remember because it's infrared can see the dust very well. Why? Because the dust are places in the Milky Way, say in the clouds. That's a cloud or molecular dust is where the material is cool, COOL, cool. Because dust cannot be hot by nature, cannot be hot. Should be cool. And anything cool will give you a lot of infrared. You cannot see a star, like our sun or any star, give up a lot of energy in infrared. So the sun gives a bit of energy in infrared, a tiny part, but dust gives up most of its electromagnetic radiation in infrared. So how is that? Maybe embedded in the dust cloud some stars, and the light will fall on it, all right? And the light itself may be a high temperature, but when it falls on the dust particle, the temperature is cooled by the dust, and then it will be radiating out in infrared, and that's where you can see, all right? So they call it the cosmic cliff, all right? Cosmic cliff in the Eta Carina Nebula, and this Eta Carina Nebula is in the constellation of Carina, meaning the keel, Keel. Keel means the bottom part of the ship, right? And its name, and this is called, it's sometimes called Gabriela Mistral Nebula. So this is called Gabriela Mistral Nebula. Why? You look at it, in 1945, big news in the what they call the world of poetry. They awarded at the end of the Second World War a Nobel Prize in Literature to what they call Gabriela Mistral, a South American woman poet and a diplomat. So she won the first South American to win a Nobel Prize in what they call in literature, right? And she's from Chile, right? So this name after her because look at her face. Actually, you look at the Gabriela Mistral's picture, this actually look like her hair, not her face. Look like her hair. So that's it. So this is it. So now many of the nebulas in the Milky Way will have this one. So if you ask me, is this exactly the real color of the picture? Maybe it has been enhanced, but basically in infrared, that's it. All right. And you see, it keep on changing because some parts where the clumping of the dust is more dense, it will clump to be even denser. But some part where you have a lot of those stars embedded in it, so the stars that were embedded in it will give out a lot of stellar wind and will evaporate a hole here. So now there's a big struggle there. The dust cloud try to collapse to form new stars, but the earlier stars born earlier will try to blow away the what they call the dust. And if you can blow away the dust, evaporate, that means some of the stars that are trying to be born become what? Stellar miscarriage. So some stars are trying to be born are not successful. But sometimes here, not many stars are born earlier, only the dust cloud is collapsing. So the stars will be successfully born. So that means even before the Earth was born, solar system was born, there was a big struggle going on. The nebula. The some parts of it were embedded in its stars that were blowing out the stellar wind. You evaporate the cloud. Stellar miscarriage, not possible, but maybe at the corner of our part of the Milky Way, where our solar system was born, not so much of the active stars were born earlier. So the stars, the clouds of gas and dust collapse to form our solar system, our Earth. Not so much. So remember, you can learn from the research paper that when you have a nebula collapse to form a star system, it's only 1% of the materials in the cloud which is the gas and the dust, successfully formed the star system. The other 99% evaporated away, blown away. Okay, so this is our Carina tips from the Webb Space Telescope. Okay, my last APOD picture for this month. Okay, so let's go back to our discover. So we asked, can you look at the APOD YouTube and the APOD what they call Facebook? Any question? No question, huh? Okay. My side,
Is there an echo?
Rain. Just mute. Okay.
No question.
Any comment from you, Rain? Final comments?
No, that's it.
Okay. Good. Boon Wei?
No.
Okay. So I just think a final,
Yes.
final comment. I call it the teaser comment. Teaser. Teaser means I give you a bit only to make you excited. But what's the news? Later only. So we hope that sometime by the beginning of next year, right? Beginning of next year, in the early half of next year, there will be another 2 more opportunities in Penang. Okay? Which means that we may have number 11 and number 12 observatory. So now in Penang, we have 10. Remember, the 10th observatory was open ceremony a few months ago by me and Dr. John Su in our Canigo Observatory, Sungai Alat, in the southern part of Penang Island. So hope that by first half of next year, another 2 observatory. You let you know, all right? Maybe we put in the news also. Maybe live broadcast. Yeah. Okay. Well, thank you, Ryan. Thank you, Boon Wei. Don't go yet. When Michael stop the broadcasting, we can still discuss.
One last thing
Yes,
to anyone who's watching. On Tuesday morning at 7:14, NASA's DART mission.
Yes.
The spacecraft will finally be crashing into Dimorphos after a 10-month journey. So for anyone who's interested,
What can you do, Ryan? Are we going to point our telescope there?
no, I'll be watching the live stream.
Live stream. Eh? Remember many years ago, I think was it in just after the year 2000, there was I think a NASA mission called Dawn or something. They crashed one of their spacecraft into one of the comet. And you know where was I? I was in Penang with my telescope, looking at the sky for so-called that comet or asteroid. I think comet, you see any splash. But right as usual, cloudy, cannot see anything. That was one earlier, got one already. Right? Something like a washing machine size object that heavy crashed into that comet. And it's going to see whether any splash there. So when it happened, many amateur astronauts on the Earth tried to observe, but they didn't see anything. So now, so space exploration is getting more and more exciting. So what is the mission objective of that, Rian?
Basically, it's to determine the viability of using a spacecraft to knock another object, in this case an asteroid, off course. So don't worry, there is no object that is coming for Earth. The asteroid that is knocking into is not currently heading for Earth. It's actually a double asteroid system, so a smaller asteroid orbiting a larger one. And what they're going to try to do is hit the smaller one and see if they can change its orbit around the bigger one. Because when an asteroid comes for Earth, it's not like the movies. We don't need to send nukes up to blow it into pieces. All we need to do is to move it slightly off course, to delay it, so that Earth can pass by and the asteroid can pass by without any collision.
And remember, I think many years ago, I think was it around 2010, I saw one NASA announcement on internet. NASA made a big announcement that as of that day, 2010, about 12 years ago, NASA have no way to deflect a large asteroid, the so-called Earth killer asteroid, to deflect it away that it will not hit the Earth later. NASA don't have the technology. 2010. Even today, I think humanity do not have the technology to blow an asteroid or object to bits or to deflect it. You cannot blow, because if you have one asteroid hitting the Earth, danger. You blow into 100 pieces, 100 objects will hit the Earth. Worse. No. So the best is to deflect it. So the idea is to deflect it far into the before it hit the Earth 20 years from now, you should start deflecting it. You deflect it and the last bonus is too near the Earth. As of 2010, there's no way humanity can do it. I think even today there's no way. So the only way you can do if there's such a case coming is what? Is to pray lah.
I beg your pardon?
Is to pray. So that please don't come in. There's no way we can do. And remember, every day there are so-called meteorites falling into the Earth's surface or small objects. Some of them will burn in the Earth's atmosphere, most of them, but some of them will fall in. So it seems a 1 meter diameter object will fall into the Earth quite often, you know. We have seen, for example, in the past 10 years, it went over like in Sulawesi, Indonesia. Suddenly, the people there saw two suns. The one, our own sun, and there's another sun in the sky for a few seconds. So it's a bright object that burns the Earth's atmosphere as bright as the sun. So 1 meter object is quite common. What about the size of a car? Maybe, I don't know, you check. It's not to say the size of a car will hit the Earth's atmosphere once in a million years. No. Once in a million years is a bigger asteroid. For example, the asteroid that killed the dinosaurs 65 million years ago is 10 kilometers big. 10 kilometers is about once every few hundred million years. But 1 kilometer size, 1 kilometer size asteroid, maybe once in a few 100,000 years. So quite dangerous. So we are still inhabiting Bombay and then in the dangerous solar neighborhood called the Earth neighborhood. A lot of things are coming in. But fortunately, in the early part of the life history of the Earth, most of the dangerous asteroids have been swept out. Not swept out by a broom, sapu, swept out by the Earth's gravity, fell onto the Earth, or other planets have deflected it or fallen into the planet. So now we are quite relatively less object, but still quite a lot. All right. Not only in the asteroid belt, so we are safe, but there are a lot of them. They cause the orbit of the Earth, ECO, Earth-causing orbit. That's why they are there. So that's why this one is to prove the technology. Now, if you can hit a small binary asteroid, one of them, the small one, can be affected. So the next one is what? More ambitious. To hit the asteroid, maybe to kick it out of the orbit of the big asteroid. And later on, a big asteroid to kick it out. We hope so. Because right now, mankind is totally exposed. No technology to avoid the collision with a big asteroid. Except one. Many years ago, I think in the 2000, now it's still the same, is asteroid Apophis. APOPHIS. Named by one of the gods of the Egyptian god. That it seems like in 2029 or something, you come close to the Earth, and then in 2036, 7 years later, it may be closer to the Earth. So this is the only one. There's a one upon don't know how many thousand chance possibility of hitting the Earth. But it's not zero. The possibility not zero is 0.00, not 0.1. So a small possibility. That's it. So very interesting. So if anyone of us here or on the Earth now, you want to save humanity, you become an asteroid deflector. Move the asteroid's orbit, go to him. Then you will be known in future for eternity as the person who saved not only humanity, save the whales, the chickens, the fishes on the planet Earth. All living things on the Earth will be saved. Possible? No. Come up with an idea. All right? Okay. Thank you. So now can we leave the thing now, but we can remain the discussion. Okay. Yeah. So thank you for everyone for attending the APOD session this month. So next month we will have maybe our Marcus Cheng may be coming in, and we try to see whether our new member of society, Dr. Andrew Tornet from the town of Lichfield in central England, maybe see whether he can join us. All right. Okay. Thank you, Michael.